Okay, if anybody has any homework questions, I can start with those. There's one thing that I wanted to say because a couple of people have already asked me about this. The question where you have the box and it's talking about the forces that you're applying to the different faces on the box. I didn't mean for this to be confusing. I probably should have just stated it more clearly. The idea was that the pressure that's provided from the pump is a gauge pressure. That's the pressure in relation to the atmospheric pressure. I don't remember which number that was, but so the idea is just this, that pumps measure pressure in comparison, in relation to the atmospheric pressure. And so I'm sure it's not always the case, but usually when you read a pressure from a pump, that's a gauge pressure. So and so then the atmospheric pressure, no, the absolute pressure is equal to the gauge pressure plus the atmospheric pressure. So in that problem, I know one part of it at least said the box is like inflated to 100 psi. The atmospheric pressure is 14 point something psi. And so you just add those two together and that gives the absolute pressure. Anybody have any homework questions? Yes. Mm-hmm. I don't have it in front of me. Yeah. Yeah.
And then it says process begins with P1 of 1 bar and V2 of 0.2 meters per kilogram. Well, that's a specific volume, right?
Yeah.
And then that's the V2. Then it asks for what the final specific volume is.
Oh, it gives it as V2 and asks for the. Do you have it in front of you? Can I? So it begins with. Yeah. So that I think that first that should be a V1. Yeah. So that's right. So P1 is equal to 1 bar. V1 is 0.2 meters cubed per kilogram. And then E2 is 0.25 bar. Okay. Any other homework questions? Okay. So now we're going to go on to first law of thermodynamics, which is conservation of energy. I'm going to excuse me. I'm going to start by going back to the way we've talked about conservation of energy up until now. How many people had a section of like a little bit of thermodynamics in a physics class? Okay, yeah. So for the people who never talked about this stuff, the only kind of conservation of energy that you've dealt with is mechanical energy, and I'm going to start with that. Start with the work energy principle, and then overly belabor the point of how the sign convention is going to change for us now. You're going to get totally sick of me beating on that. You're going to roll your eyes, and then on the first test, half of you are going to do it wrong. So here's what you've done in mechanics. Dealing with particles. Energy is kinetic energy, and that's just 1/2 mv squared. You can think of energy as a state, as a property. It's I guess, property. It represents a particle at an instant. And then there's something that relates to processes, changes in energy, and that's work. And work is defined as the integral along a path from location S1 to S2 of the force vector dotted with an increment along the path. So that's a line integral. Question? So energy is a property. Work relates to a process. So there's no such thing as like how much work does a thing have at this instant? That doesn't make any sense. Work only happens between two instants. And if you have rigid bodies, you also have that there's rotational kinetic energy that's equal to 1/2 times the moment of inertia about the center of mass times the angular velocity squared. I guess let's make this velocity of the center of mass up here, just so those two go together. And then you also have work that can be applied by point couples, point torques. That's equal to the integral from θ1 to θ2 of the moment times d theta. And these go together. So work and energy go together in the work energy principle. And that says W is equal to the change in kinetic energy. And all the other forms of conservation of energy that you dealt with in mechanics are just different versions of this, including anything that has to do with potential energy. This is a complete, this is the most general statement of conservation of energy for mechanical systems. So what this is saying is, since work is the only way to change energy, it says the change in energy is equal to the later energy minus the earlier energy. And when you think about it that way, it seems pretty obvious. And the thing to notice here is that W is positive if energy is added to the chosen system by the work. If you look at, the form of this, if you think of this as the later kinetic energy minus the earlier kinetic energy, this equation means that if you have more kinetic energy later than you did earlier, you have a positive value for work. So that's energy added to the system. In thermodynamics, W will have the opposite meaning. And we'll talk about that more when we get to that. But I'm going to just spend some time talking about conservation of energy and mechanics. Power is defined as the time derivative of the work. I don't know if everybody's seen the dot notation for derivatives with respect to time, but that means a total derivative with respect to time. So that means dw dt. So if you use the dot notation, you can't use it to indicate a derivative with respect to x or something. It's always with respect to time. And with, yes? Yeah, so let me write this so I don't forget. Okay, so that's equal to the force times the velocity of that point. If there are multiple variables, so if you have a function of x, y, z, then f dot is df dx times dx dt plus partial of f with respect to y, dy dt, yeah, changeable. And you can see this relationship if you start with, if work is equal to an integral of f dotted with ds, the chain rule says ds is equal to ds dt times dt. And so you can rewrite work as f dotted with ds dt dt. And ds dt is the velocity of that point, so f dotted with the velocity dt. And now taking the time derivative of a time integral just gives you the integrand back. So power is equal to d dt of f dot v dt. You get f dot v. Okay, so if the work energy principle is the most general expression of conservation of mechanical work, then the question is, what's potential energy? Potential energy doesn't show up at all in the work energy principle, but we're used to dealing with it. Well, it turns out that if you have a force field and the meaning of that is that, so force is a field of anything, an electric field, a magnetic field, a poppy field, like in Wizard of Oz. Like, what's special about a poppy field? The idea is that no matter where you go, there's like a poppy there waiting for you, you know? And if you leave and go around and come back to that same spot, it's not a new poppy, it's the same one, you know? And that's the same thing with force fields, electric fields, magnetic fields. You can think of like at a single location, there's a force there waiting for you. Okay, that's another way of saying that the force is conservative. All you need to know what the force is the location, the object's location. So if you have a force field, knowing the object's location is enough to know what force is applied. These are called conservative forces, and so something being a conservative force and the force being able to be represented by a force field those are interchangeable terms. They mean the same thing. Okay, so what are some conservative forces? Well, you just have to think of forces that only depend on an object's location. They don't have anything to do with how the object got to that location. The simplest example is gravity. Usually, as long as we're close to the Earth, gravity is even simpler than it needs to be a force field, because we don't even have to know the object's location. We just say the force is mg down, no matter where we are, right? And so the question is, if we specify an object and I give you the location, is that enough for you to tell me what the force is? And the answer is yes. And with this, you don't even have to wait for me to give you the location. Let's think about, some other forces. What about a normal force? So now we put this object on the table. I tell you the location here. You know that it's a stapler, you know the properties of it, the mass and everything. Is that enough? Is that location enough for you to know the normal force that's applied? You might think so at first, but if I, press on it, the normal force is increased. If the slope of this table changes, the normal force direction changes. So a normal force is not conservative. Okay. So gravity is, a normal force isn't. Friction obviously isn't, because if it's sliding this way, the friction force is that way. If it's sliding the other way, the friction force is that way, even at the same location. The other, I think most likely you dealt primarily with two types of conservative forces in physics one. One was gravity, and what was the other one? Spring forces, probably, I would think. So the way that works is, first you have to specify the object and position the spring. So let's say there's a spring connecting the wall to this object here. Okay? And you know the properties of the spring and everything. Now the question is it enough information if I tell you the location of this object for you to tell me the force the spring applies to it? And it is, if I pull it back this way, you use kx to figure out the force pulling it back. If I push it this way, kx tells you the force pushing against it. And with the mathematical approach we use for springs, that force doesn't change depending on the path. I could do this for a while and then come back here, and the force is the same as if I pulled it here and then got here, So those are, spring forces and elastic forces in anything. Like you bend a steel bar, don't bend it to the point where it has permanent deformation, but just a little bit. And you unload it, it goes back into position. All of those kind of elastic forces are conservative forces. And for a conservative force, potential energy function, and that's just a name, potential energy function it depends only on location. Only on the object's location. Such that the work done by that force, by that conservative force, is equal to the negative change in potential energy. So again, this is the work done on the object. So notice that potential energy only exists for conservative forces. So you could think of these three things as being interchangeable: the existence of a potential energy function, representation of a force as a force field, and the name conservative. Okay, those all mean the same thing. But the benefit of this, if the force is conservative, the benefit of thinking about it in terms of potential energy is that you can calculate the work done by the force by a force between locations 1 and 2 just by evaluating a function at those 2 locations. So let's think of it as, evaluate this function potential. Don't write it like that. By evaluating this function at 1 and 2 instead of calculating that line integral. And who here likes calculating line integrals? Okay. Well, anybody who likes it, you can think about it, but for the rest of you who are lazy, potential energy is just a nice approach when it's available to you. When it's not available to you is anytime you have a non-conservative force. It is kind of fun. You can. But you know what's more fun than calculating line integrals? Seeing someone calculating a line integral and being like, hey, dummy, you could have just evaluated that potential energy function at 2 spots, So let's do an example. See how this works. So let's say we have an elevator hanging from a cable. The elevator has a mass of 500 kilograms. Bless you. And for A and B, let's say we want to calculate the work done on the elevator by gravity as the elevator rises 4 meters. And we're going to do it 2 ways. We're first going to calculate the line integral. We're going to use work is equal to the integral S1 to S2 of the force dotted with ds. This ds is a vector. Oh, I didn't detail that. I guess maybe we'll see it in the example, but that ds is a vector. What's the direction of that vector ds? What am I talking about there? Oh, well, in this case, it is going to be upward. In general, it's always tangent to the path that the thing's traveling. Okay. And then second, we're going to do it with a potential energy approach. Given that the potential energy due to gravity is mgh. So let's do those first, and then we'll talk about that, and then I'll give 2 other problems using the work energy principle related to this. Okay, so First, let's do the line integral. So the idea is, so work is equal to the integral from, so the path that this thing is taking is going from a height of something to a height 4 meters higher, right? Is that what I said, 4? So we might as well say that our zero height is at the lowest position and just evaluate this from 0 to 4 meters. The force of gravity is mg acting down. So that's going to be 500 times 9.81. And then ds is parallel to this force at every instant. What's the dot product between the weight force and this ds as it rises from 0 to 4? Yeah, cosine of 180. And so these are going in the opposite directions, which means that that line integral has to have a negative sign. You see that? Do you feel it? You feel where that negative sign comes from? That's right, because it's fighting against gravity. Okay, so if ds and f have a positive dot product, if that line integral gives you a positive dot product, that means that they're closer than 90 degrees. So evaluate this integral, you get negative 4905 times s, and we're going to evaluate that from 0 to 4. And so you get 4 times 4905. What does that give you? $19,620. And what are the units here? Yeah, we've done everything in SI units, so the units are joules. What does it mean? What does the negative sign mean? That would be the case if we were using the thermodynamics sign convention, but we're not yet. So this is saying that as the elevator rises, gravity is fighting against that motion, and in other words, stripping energy away from it. Okay, whatever is lifting the elevator up has to overcome gravity trying to slow it down. We can't say that for sure yet because we don't have enough information, but we know that so there was energy applied by the cable to lift it, and it had to be enough energy to overcome gravity trying to strip this much energy away from the system, or successfully stripping this much energy away from the system. Okay, 19,620. So now a potential energy approach. The work is equal to the negative change in potential energy. And so that's negative of mgh at the later instant. That's 4905 4 meters. Minus the potential energy at the earlier instant, that's 4905 times 0. So you get the same thing, negative 19,620. And this approach maybe sort of explains why there's this connection between potential energy and conservative forces. The idea of conservative forces is that you know the force if you know the location, right? Whatever happens in between doesn't matter. And so you can calculate the work that you do just based entirely on the two endpoints. All the stuff that happens in the middle doesn't matter, okay? If you don't have that property, obviously this line integral can very easily depend on the whole path it takes. And so this gets messy for non-conservative forces. For conservative forces, just use the endpoints. No. So now here's two more questions. If the only other force on the elevator is the cable force, and the elevator starts and ends at rest, what's the work applied to the elevator by the cable? And then the second one, the elevator starts going down at 2 meters per second and ends going up at 5 meters per second. What's the work done by the cable? So for this one, we're going to use the work energy principle. The work energy principle says add up all of the work applied to the chosen object, and that has to be equal to the kinetic energy at the later instant minus the kinetic energy at the earlier instant. And this work is, you just have to calculate the work done by each force. So that is work done by the cable plus work done by gravity, and that's equal to the difference in kinetic energies. Well, it's starting out for part C at rest and ending at rest, so those are going to go away. And so the work done by the cable is the negative work done by gravity. And we just calculated that the work done by gravity was negative 19,000 something, 620. So the work done by the cable is positive 19,620 joules. And for part D, the only difference between C and D is now we have kinetic energies. So for D, we have that the work done by the cable plus the work done by gravity is equal to the kinetic energy at the later instant. So that's 1/2 times 500 times 5 squared. And the kinetic energy, minus the kinetic energy at the earlier instant, 1/2 times 500 times 2 squared. Can someone calculate what the right side of that is? $5,250. Okay, so then in this case, the work done by the cable is negative of negative 19,620 plus 5,250 is equal to, can I do that? Maybe 24,870 joules. So when you see like the form of conservation of energy that you're most used to, where you add up the kinetic plus potential energy at instant 1 and set it equal to kinetic plus potential at instant 2. That's a special case of the work energy principle where the only forces you have are conservative. And you can just, I should make you derive that. That'd be a good idea. It's not that hard. So now I want to talk about, I'm going to talk about two types of work that are going to come up pretty often in these thermodynamic systems. And then we'll switch over to the new convention, the new sign convention. And from that point forward, we're going to use the new sign convention. So these are two work calculations we'll use in thermodynamic systems. The first one is extension of a solid bar. So let's say we have the solid bar that's fixed to the ground, and you have an applied force T at the end that's stretching it a tiny little amount. I should specify here that we're talking about within its elastic range. This is the kind of stuff that we talk about in D-form when you take that. Um, so the idea is that if you stretch a piece of metal, at first, the first tiny little bit you stretch it, if you let go of that load, it'll immediately spring back to its original length. As long as that'll happen, you're in the elastic range. Like, what does elastic mean to you? Like in everyday speech, what does elastic mean? Yeah, that's how most people think of it, is like it's stretchy, but it's not the stretch exactly that makes it elastic. It's the fact that after you stretch it, it springs back. So like if you think of like Play-Doh is stretchy, you can stretch it out, but when you let go, it's not elastic, because when you let go, it's still long, you know? When your elastic waistband goes out on your underwear, you can still stretch it. It's just not very good as underwear, because then it doesn't come back, you know? So the elastic is the bouncing back. Well, um, the total tension applied at the end is equal to this is the Greek letter sigma. That stands for the normal stress in this material times the cross-sectional area. So this is called the normal stress in the bar. And this A is the cross-sectional area of the bar. And so the work done is equal to the integral from x1 to x2 of the force dotted with that tangent to the path, and so you come up with this: the normal stress times the area dx, and the sign is determined by the sign convention. The other thing that we're going to use pretty often is the power and the work transmitted by a point couple. And by a point couple, you can just think of that as a single applied torque, like you might apply with a screwdriver. If this wall just happened to have a slot, so I could put a screwdriver in it, it wasn't attached to a screw or anything, it was just attached to the board, and I put a screwdriver in there and twisted it, I'd be applying a point couple to the board, you know, that would tend to rotate it this way if other things didn't counteract that. The power is the time derivative of the work. And remember that power is equal to force dotted with velocity, right? I won't go into all the geometric arguments. What's happening? Am I going to? It sort of feels like it. No. So basically, you can think of the forces, take my word for it, all the forces and velocities are perpendicular to each other. And so we end up just forces and velocities. No, they're parallel to each other. They're in the same direction. And so when you take that dot product, you just get, okay, you get force times velocity like that. The force you can think of as the torque divided by the moment arm. The velocity of each of those points is the angular velocity times the radius of the basically the moment arm of those forces. And when you cancel all those out, you get the moment times the angular velocity. And for the work, I already mentioned this one, but the work is equal to the integral from theta 1 to theta 2 of the moment d theta. And again, the signs are determined by which sign convention you're using, what body you're isolating, that kind of stuff. All right, so this is the end of using the mechanics sign convention. All of that whole description of that was just supposed to be kind of a overview of stuff that you've learned before. But for all of this stuff above, all of the energy discussion above, W meant work applied to the chosen system. From this point on in this class, we'll switch to the thermodynamic sign convention. And that is that work is work applied to the surroundings by the chosen system. It just comes out to mean that work with the thermodynamic sign convention is negative of the work with the mechanics sign convention.
I guess it seems obvious to wonder why do we use this thermodynamics.
Yes. As best as I can figure, this is, if this isn't why, it at least is a good memory device. So it's useful whether this is how it developed or not. So think about it this way. The chosen system in a thermodynamic problem is often a gas. It's being used to do external work. You know, like a heat engine. Um, in this case, work in the thermodynamic sense, that W in the thermodynamic sign convention is a positive number. Okay, so if you're heating something up to make it do work on wheels or machinery or whatever, your W that we use in thermodynamics is positive. Any questions about any of that mechanical energy stuff or about this sign convention? Yes.
Sometimes just use
Yeah. I think we're not going to use that because lowercase u is internal energy. Well, and actually, yeah, so U is always going to be internal energy. So we can't use that. Yes, I've used that before too. Oh, yeah. Capital U is going to be internal energy. The extensive version of internal energy in lowercase is going to be the intensive, so that's not available to us really. Okay, so there's one other type of work that we're going to deal with all the time. First, I wanted to introduce the new sign convention, but this is the work that's done by a gas and expansion. So if you think about a cylinder and a piston, so there's a cross section of the cylinder. And here's the piston inside. And this is the gas that we're talking about. And let's say that this is, well, that's a length. I don't really want that to be a length. I want it to be a cross-sectional area. Let's call that the area A. And let's call this the height H. What direction is the force that gas pressure is applying to the piston? Up. And if the pressure is lower or whatever, like, so this is something that can sometimes get a little confusing. It's easy to think of basically anything that you've ever thought of as suction. Try not to think about that. There's no such thing as suction. Okay, all there is pressure differentials across this. If you evacuated this chamber, it would feel like you're creating a suction that's pulling that down, but all you're doing is making the pressure in here lower than the atmospheric pressure. And so the atmospheric pressure is the thing that's squishing it or whatever. Okay? And so even if you got this almost all the way to zero pressure, it's still positive pressure. You know, even if it feels like there's a strong suction, this gas is actually has a positive pressure. And like you said, the direction of that force is pushing up on that piston. And so the work done by the gas is equal to, we're going to use the integral definition of work. We're going to go from the initial height to the later height. The force is the pressure times that cross-sectional area. And the increment of motion along, like that line integral ds, is dh.
How you came up with
Is what?
Are you just gonna ask lowercase b to make it obvious?
Oh yeah. I'll make it right. That's how I'll try to do it. That's yes. I will. Yes, I will. Okay, so rewrite this. This is H1, H2, P, A, BH. And you can re-express A, BH, that little increment, that little change in the height of that piston, dV, exactly. And so our definition for the work done by the gas on the piston is the integral from volume 1 to volume 2 pressure dV. This is the work on the surroundings by the gas and this applies to any change in volume. Even though I showed it for a piston and a cylinder, it would apply to a balloon expanding or whatever. So any volume expansion, not just a piston in a cylinder. And then this last thing I'll give special attention to. Notice that what this means is W, remember that's our new thermodynamic W. Always positive if a gas is expanding. And negative if a gas is contracting, being compressed.
Two questions. That's just due to the fact that volumes either increasing or decreasing. That's what's giving the assignment.
Yes.
And then the dV that absorbs the vector notation of the dV.
Yes, because the pressure is always perpendicular to the direction of the volume expansion at every point in the wall. And so that takes care of the dot product. And it's easiest to think of, even though even though it can work with a balloon or whatever, it's easiest to think of all that kind of stuff with a piston. So if you're trying to think through it, it usually is an applicable, like you can usually, in every case I've come across, thinking about it that way gives you all the details you need to come up with the general way that it works. Okay, here's an example. So let's say that a gas has a pressure of 1.30 times 10 to the 5th pascals at 0.35 meters cubed of volume. Then the temperature is reduced as the pressure is held constant. Okay, so let's think about this for a second. Imagine a gas inside a cylinder that starts out with a certain pressure and volume. And imagine that you don't move the piston at all for a second, okay? But you reduce the temperature in the gas. What's going to happen to the pressure of the gas when you reduce the temperature? Yeah, the pressure is going to decrease. And so in order to keep the pressure constant, you have to, the piston has to go down. You have to decrease that volume. And so what's going to happen as the temperature reduces, if you hold the pressure constant, is that the volume has to reduce. So temperature is reduced as pressure is held constant, comma, and the volume during that time is reduced to 0.2 meters squared. Yeah, meters squared times meters. I thought that was implied. What's the work done by the gas? Well, the work is equal to the integral from volume 1 to volume 2 of the pressure dV. And in general, that pressure changes at the whole path along that volume change. But in this case, we're holding the pressure constant. So this is the integral from 0.35 to 0.2 of 1.30 times 10 to the 5th dV. And that's 1.3 times 10 to the 5th times the quantity 0.2 minus 0.35. And so that's negative 19,500 joules. Does the sign of this answer make sense? Yeah, the volume was reduced, so work has to be negative. let's stop there. And so the next thing we'll have to do is just figure out a couple of ways to approach cases where, so our life would be easy as far as calculating work if all processes were constant pressure, but it would be it'd be unnecessarily hard to do, practically speaking. So we need ways to calculate the work when when that pressure is changing during the process. And so we'll talk about that a little bit next time. Okay.